everyone, Mrs. Pasega here, and today we're working on the Unit 7 review packet. Because this is set up a little bit differently than the ones we've previously been doing on formative, I want to point out a few things. First off, make sure you're still doing all these problems first, then go check the key. Then watch this video. Don't use this video in place of you trying it yourself. Next, notice that all the objectives here are going to correspond to one page at a time. So my first page is going to have problems that hit on all of these objectives. Let's say you had trouble on the first page. Then you would be like, oh yeah, maybe I need to work on calculating resistance from a graph, right? That way you can start to narrow down what things you need to review and what things you're pretty good at. So let's get started. To calculate resistance from a graph, you need to pick some point on this graph. I'm going to pick the point 6 volts and 1.5 amps and calculate the resistance using Ohm's law. So I get a point for writing down my equation. Now I substitute. The current is 1.5, the voltage is 6, and so my resistance is whatever 6 divided by 1.5 is. That's 4 ohms. Now, if you had a wire with twice the resistance, this would need to have half the current. So at every data point here, I would have half of the current that was achieved by the original wire. So where 6 volts previously caused 1.5 amps, this would only cause 7.5 amps. Repeating this all the way across, I see that at 12 volts, this would only get 1.5 amps, and my line should be a direct relationship, still going through the origin, but having less current because it had more resistance. That's your inverse relationship from Ohm's law. Right, this one, calculate the total amount of charge given the current and time. So when I'm picking out my equation here, equations that have current and charge and time look like this. So I'm going to solve for Q. That's the total charge. That's 3.5 amps. A time of 1 minute is really 60 seconds. And so my Q, and you can feel free to drop the deltas here, Q would be 3.5 times 60, or 210 coulombs. A special note, you do need to know what an amp means. 3.5 amps means that there are 3.5 coulombs of charge that pass through every second. So if there are 60 seconds at 3.5 coulombs per second, you multiply them together. So you do need to know that 1 amp is equal to 1 coulomb per second of charge that flows through. 1D, which of the following statements about DC electrical circuits is false? Well, first off, I know it's not current is protons. Current is electrons moving. So it can't, oh, this one is false. I'm going to circle that. But let's just check that the other ones are true. So is it true that electrons move from the negative end of the battery to the positive? Check. Electrons move in a circuit because they're less massive than protons, and they exist on the outer reaches of your atom, so they're easier to move. The electrons move very slow. A thing you need to know is the electric field moves very fast. So the field is fast, the electrons themselves are slow. Okay. Finally, on page 1, a current is 12 amps. How does that current change if the voltage is doubled and the resistance is reduced? So first off, I'm going to write Ohm's law. Current depends on voltage and resistance. The original current is 12 amps. Now let's make a new scenario. In my new scenario, I have twice the voltage. But making 1/3 of the resistance actually means I have more current. Think I'm like dividing by a third. Dividing by a fraction is the same thing as multiplying by its reciprocal. So I have actually 6 times more current than I did before. Because I have 6 times more current than I originally did, I have 6 times more than 12. So 6 times more than 12 is 6 times 12, and that's 72 amps. My new current is 72 amps. Ta-da! Okay, electrical resistance. This page is the one that goes along with these standards. Okay, so we want to explain the cause of electrical resistance in a wire, including energy transformations, and describe the factors that affect the resistance of a wire: area, length, and resistivity. So let's do it. We actually did this lab, if you remember. Wire A has higher resistance because as the length of the wire increases, the resistance of the wire increases. I'll physically write more on this copy on my physical answer key that you'll see later. But for now, a longer length means more resistance because think of this as wire A, the electrons have more obstacles to get through. Resistance is caused by electrons interacting with the atoms they come in contact with. So if there's a lot of little collisions in this wire, and because it's a longer wire, it'll have more resistance. If I have 2 wires of equal length, but more thickness, this is changing the area of the wire. And as area increases, resistance decreases. That's an inverse relationship. So A still has the higher resistance. Wire B has more area, so it has less resistance because there's more space for the electrons to move. They're not interacting with each other as much, so there's not as much electrical resistance. Now, metals are good conductors of electricity because they are having very loosely held electrons. They don't have many more electrons than protons. That's not true, because then they'd just be ions. They clearly have electrons, so that's not true. But electrons are tightly held. That is an insulator property, not a conductor. So the electrons are loosely held. That means they're free to move away from their little proton buddies in the atoms. Now let's look at question C. This is another proportions problem. So the original resistance, rho LA, if I write down my original equation, is 10 ohms. And in my new scenario, it's still the same material, but it has 1/3 of the length, so the electrons don't have to go as far. That's easier. But 3 strands in parallel actually has 3 times the area. And to help you picture it, I want you to imagine taking a long, skinny wire like this, right? This is my original. My original was 10 ohms. But now you fold it 3 times. So now it's 1/3 of the length and 3 times the area. So the electrons don't have to go as far. That makes it easier. That's a 1/3 here. But the area is 3 times as big because you folded it over 3 times. So that actually makes it 1/9 the resistance, right? Rearranging this new equation says I have 1/9 times the original resistance. And 1/9 of 10, well, I can do that. 1/9 of 10 is 1.111 ohms. So 1/9 of 10 ohms is 1.1. Finally, a round wire has a resistance of 12 ohms. It's now replaced with a mirror, something with twice the resistivity, twice the length, and twice the diameter. Oh, we are being tricky. Okay, so let's write this out. So still write the same equation, but with a small modification. Instead of using A for area, can you use pi r squared for area of a circle? Because if you do, you'll notice that having twice the resistivity, that's 2 rho, twice the length, and twice the diameter. When you change the diameter, you also double the radius. So doubling the radius, if I rearrange this now, I have 4 over 4 times the original resistance. So if my original resistance is 12, yeah, it's still 12. 4 over 4 is 1, so I have 1 times the original. That's still 12 ohms. So even though I made it a more resistive wire and a longer wire, doubling the diameter actually quadrupled the area, and so there was no change to the resistance. Next, let's deal with series circuits. In series circuits, you should be able to tell me what is a series circuit. Calculate its equivalent resistance, voltage, and current, and describe the effect of adding more resistors in series to the total current, it decreases, and the power, it also decreases, of a circuit. So, first off, let's draw some conventional current. Conventional current goes from positive to negative. Yay! Now let us find the equivalent resistance. I'm just going to go along with here, and then I show my work and use that to fill in the boxes. We'll be good. So my equivalent resistance in series is achieved by adding together the resistances. So that is 2 plus 3 plus 4. That is 9 ohms. So I got box H using the equivalent resistance for series. For box G, I used Ohm's law. Across every row, the current has to be caused by the voltage over resistance. So in this case, the voltage was 18, the equivalent resistance is 9, so the total current is 2. If you want, you can also explain that you used Ohm's law. Now, box C, I need to get into directly. There's actually like 2 steps here. First, I need to notice that this is in series. So if 2 amps leaves the battery, it must flow through each resistor because there's only one path. So 2's all the way up. How I got the voltage drop from R2 then is across this row, the voltage is current times resistance. I knew the current was 2 because it's in series, and the resistance was 3 because that was given in the problem. So this used up 6 volts. Now, all I have to do is explain the rest of the circuit. So across here, that's 4, across here, that's 8, and maybe over here, I would say this is Ohm's law. Because I used either I is equal to V over R or V is equal to I times R. Now this is a straight up calculation for F. I don't need to explain anything. I would just apply my power equation. Power is current times voltage. So in this case, the current is 2 amps, the voltage is 18, that is 36 watts. Now, the energy in joules in 15 minutes. Remember that a watt is a joule per second. So if there are 15 minutes worth of seconds, I'd be doing 36 times 15 minutes worth of seconds. That's where my power equation versus energy comes from. Energy is power times time. The power is 36 watts, 36 joules per second. That's what a watt is. Times 15 minutes worth of seconds. 15 minutes worth of seconds is 900 seconds. That makes 32,400 joules. On the diagram above, draw a dotted line representing a short circuit that would turn off all three resistors. For a short, all you need to draw is some sort of path that starts and ends on the battery and skips every resistor. So let's draw up one. How about there? That would be a short circuit, because now all the electrons would go through here without hitting any resistors. There's plenty of other possibilities you can draw, so if yours doesn't look like mine, that is okay. Next, we are on to parallel. And from a parallel circuit, you should be able to describe what a parallel circuit is, calculate its equivalent resistance, voltage, and current, and describe the effect of adding more resistors in parallel to the total current it increases and power it increases of a circuit. So let's take a look at my system. It says in the diagram, draw the direction of electron flow. Electrons flow from negative to positive, and it actually makes three little independent loops here, just like that. Now, it says to calculate all the components of the box, but just like before, I'm going to go show my work here and use that to fill in the box. And guys, as a hint, I'm asking them in the order you would solve them. It's almost like I planned this. So first, equivalent resistance in parallel. That's Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3 inverse. Or in this case, that's 24 inverse plus 8 inverse plus 12 inverse. All inverted. And just like I did in class, I'm going to substitute into my calculator those values, 24 inverse plus 8 inverse plus 12 inverse. I'm going to do those first. So that's 0.25. But that's 0.25 inverse. So I'm going to hit inverse one more time to make 4 ohms. And we do that double check at the end, remember? Is 4 ohms smaller than the smallest resistance? Yeah. 4 ohms is smaller than 8, so hey, my value for H makes sense. I calculated equivalent resistance for parallel using the parallel equation. Now, how I got the total current is Ohm's law across the bottom row. Ohm's law says that the current is equal to voltage over resistance, true for the whole circuit as well as every individual element within a circuit. So that's 24 over 4, or 6 amps. However, I'm not going to go put 6s all up on the other resistors, because that 6 amps, let's say this is 6 here, reaches junctions and splits up. So each one of these resistors should have less than 6 amps because it only grabs a portion of the incoming current. Cool, so let's get the voltage drops. In parallel, the rule is all of these items have the same voltage drop. That's because along any path, the battery puts in 24 volts. It only encounters one resistor per path. It must lose 24 volts so that energy is conserved. This is called Kirchhoff's loop law. It also explains why in parallel, things have the same voltage. So what did I use for this? I used the parallel rule, and in parallel, they have all the same voltage as each other. So how do I get the current through R2 then? Is across this row, it has to obey Ohm's law. Ohm's law I could either write as I is V over R, or V is I times R. So I'll just solve it this way for funsies. In this case, across row 2, that's 24 equals current times 8. Therefore, the 3 dots means therefore, 24 over 8 equals 3 amps. Now, let's grab the rest of them while we're here. The rest of the currents then are 1 and 2, so that Ohm's law is obeyed across every single row. So, in what ways is this like a household circuit? Well, this is like a household circuit because households are largely in parallel. How is it dissimilar to a household circuit? Well, a household circuit should have an alternating current source. So that's one difference. And it should also be 120 volts, at least for most outlets in regular homes. So I will write out that answer later so you can get a nice neat answer. Finally, if I added a fourth branch, how would the equivalent resistance change? How would the current change? How would the power change? So I'm going to write this down in symbols and write a better answer later. If a fourth branch were added, then the equivalent resistance would decrease. That is a key finding in parallel. More resistors actually means less resistance. Because every time you add a new path, that makes it easier for electrons to flow. So more paths, less resistance. If it's easier for electrons to flow, you get more current. And that actually means you get more power also. This could be problematic because if you have too little resistance and too much current, well, you could light the wires on fire. You could cause something to melt that shouldn't be melting, right? This is called an overload, when a parallel circuit has too little resistance because you put too much stuff on it. That is fundamentally different than a short circuit, where a short circuit skips all the interactions with resistors. But speaking of which, let's get to some drawing so we can talk about how to keep circuits safe. There we go. Now you can see it. Okay, so let's draw a circuit with 3 1.5 volt batteries. It is convention that if you know the total voltage of your system, so that's 4.5, you write the total voltage instead of putting 1.53 times. To double check I have the right symbol, it should have 3 longer sides and 3 shorter sides. It is connected with a 6 ohm light bulb. So I'm looking for this cupcake symbol here. A 2 ohm resistor. And an open switch. Now, because it's an open switch, I don't know if that's a great choice, because if it's an open switch, I can't draw the direction of electron flow because the electrons are not flowing. If the electrons were flowing, they'd be flowing that way, counterclockwise, because they would flow from negative to positive. For 5b, if bulb A is removed from the circuit and not replaced, the current stops everywhere in the circuit. It doesn't leak out like a water would leak out of a broken pipe. Oh, I read that wrong. Haha, I'm not editing this. I'll fix this right now. If bulb A is removed from the circuit, that would create an open path right here. However, the electrons could still make it through the rest of the circuit. They could still go through D and C and all the way back to the battery. So actually, the current continues unbroken through the remaining branches. I read that too quickly. If bulb A is removed and not replaced, the rest of the circuit keeps going. Yes. All right, so next, Which two circuit elements have the same current as each other? C and D. If we start imagining our current as leaving the battery, 100% of the current goes through D. 100% of the current goes through C. So both of those need to have the same current as each other. Whereas A and B are going to split the current. Right now, B has current. Maybe A doesn't. But let's assume that the bulb hasn't been removed yet. Then this would go through. A and B would split the current. And so the total current would return to the battery. The two that have the same voltage drop as each other are A and B because they are in parallel. That is, in fact, the parallel rule. Things in parallel with each other have the same voltage. So, it says draw the conventional current on the diagram, and I wish I had seen that because I actually drew the direction of electron flow. If I want to draw conventional current, I should be drawing this from positive to negative. So actually, if I want to do this right, imagine my current leaves the positive terminal of the battery, splits up into two paths, recombines, all goes through C, all goes through D. Conventional current goes from positive to negative. So we'll correct that right now. So conventional current should be going clockwise in this circuit. All right, for F, draw a jumper wire that would turn off both C and D, but keep all bulbs A and B running. Well, actually, I can use this one right here. Here's my jumper. Let's imagine the conventional current goes from positive to negative, so it's going over these paths, and it reaches the junction here. When it has the choice to go through a zero resistance path, the electrons take it, completing our circuit. This makes bulbs C and D turn off, while A and B stay on. A fuse needs to be drawn next to your power supply. So I'm going to draw my fuse here. It's got to be next to my power supply in some place that it's not going to have any resistors between the power supply and it. Don't draw your fuse along your shorts or jumpers. I'm looking for placement adjacent to your power supply. So, how does a fuse keep this circuit safe? Explain specifically how your placement in 5G protects the circuit. So, in this case, my placement is next to the battery. This protects the circuit because the total current flows through the battery. Cutting off the circuit at its source prevents current from going anywhere else in the circuit. This fuse would melt, causing an open circuit, and if it were open, then current would flow through. None of it. All right, so now we are on to Objective 6 and household wiring. This one is also called Electrical Power and Energy, but all of its standards are on this page. So on this page, you should be able to evaluate current in a household circuit, determine the energy in kilowatt hours, and explain that household circuits are in parallel so that if one item is broken, the rest stay on. It also gets a bonus feature that every outlet can have the same voltage because items in parallel have the same voltage as each other. So I've kind of explained 6A already. I'll write that full answer out in the answer key, but basically, appliances are parallel so that if one item breaks, the rest keeps its current. How to calculate current through a blender. The 30 ohm blender, that's this one, and the 1,400 watt microwave. Oh, I am so tricky to you. Because in 6b, you're going to use Ohm's law. No big deal. I know you're going to get this one. You're going to be like, oh, great, 120 over 30, math in my head, that is 4 amps. And then you're going to look at current through the microwave and be like, what do I do with that? I'll tell you what you do with that. You know the power, so go get the current. You know the power is 1,440. You know the voltage is 120. So divide to get I. 1,440 watts divided by 120 volts. Sorry, calculators, right? It's 12. So that would be 12 amps. So the question, will this circuit fail if both appliances are on? Yes, it will. Because check this out. Imagine my fuse is right here next to the power supply, protecting us from rogue currents. Close the door. Let's say this current has 4 amps this way and 12 amps this way. How many amps are going to run through that fuse then, my friends? Yeah, 16 amps would go through. That's what junction law says. And hey, does 16 amps melt this fuse? It does, in fact, melt this fuse. So I'll write this answer out further later. The fuse will blow if both appliances are on at the same time. That's because this circuit would pull 16 amps from the outlet, and that would melt if the limit was 15. So let's say we fix this up, and now we're just dealing with the blender. We are not turning on the blender and microwave together. The power rating of the blender, we're going to do power is current times voltage. That is 4 amps times 120 volts equals 480 watts. In joules, in one day, I would do energy as power times time. So that's 480 watts times 1 day's worth of seconds. Well, that's quite a lot of seconds. That is 86,400 seconds. At 480 joules per each of those seconds gives me this big number of joules. Cool. So that's 41,472,000 joules per day. But to be fair, I read this problem wrong. It's not a whole day's worth of blender. You're only using it for 5 minutes, right? I probably don't use my blender for 24 hours straight. That would be not useful. So hold on, let me fix that. 5 minutes, that's 300 seconds. That's a more reasonable answer. So 300 seconds at 480 joules per second is 144,000 watts, or 144,000 joules. So much better. Now, an equation that you use the same way, but get a different type of answer. Let's say we need to get kilowatts. A kilowatt is a big unit of energy, and that's what your electrical bill is measured in. That's why we're calculating it today. I'm still going to do power times time, but I need you to take the power in kilowatts times the time in hours. This time we're switching it over to the microwave. So the microwave is 1.44 kilowatts. And if you're wondering where I get this number, it's 1,440 watts, but divide by 1,000 to get kilowatts, times 16 hours. That's a lot of microwaving. So it's 1.44 times 16 for 23.04 kilowatt hours worth of electrical energy. And if each of those units of electrical energy cost 27 cents, then I'm going to multiply together to get cost. So times 27 cents is $6.22 to use my microwave per month. I feel like that's worth it. I make a lot of things in the microwave. Which brings us to the last page, which actually has both how to do circuit Sudokus and equivalent resistance. So, how to do a circuit Sudoku. For this, be able to solve for voltage and current, explain that conservation of energy goes with voltage law or loop law. So how about we put that in as loop or voltage, both are the same law. Explain that conservation of charge goes with the current law, that's the junction rule, and use all 5 patterns to complete the circuit Sudoku. Then we'll finish up with equivalent resistance, and that's it. So let's do this circuit Sudoku. Across the first row, 16 equals 4 times 4, so the resistance in box A is 4. Now I see that I have 2 currents in the center column, but only 1 voltage. So it's going to be more productive for me to deal with the currents first. Imagine I have a 4 amp current going through R1, and that 4 amp current goes into this junction. 1 amp of current goes through R3 right here. 1 amp. That must mean 3 amps of current go through R2, because 4 is equal to 3 plus 1. That 3 amp of current combines with the other 1 amp to make 4 amps total, meaning that R4 must get 4 amps of current. And so must the battery, and so must R1, and so on and so on. The 4 amp total temporarily splits up between these 2 parallel paths, but all in all has 4 amps total. So now, because I know some currents and resistances, I can go find my missing voltages. 3 times 4 is 12 to get my voltage. 4 times 2 is 8 to get my voltage. I see that R2 and R3 are in parallel with each other. That means they have the same voltage as each other. And then I can use loop rule to get the total amount of voltage from the supply. Now, loop rule is super important because it deals with conservation of energy. So even though I didn't show all my work out here, I will do it later. For part H, let's say I do loop rule. This says the voltage, and therefore the energy put out by the supply, gets used up by all the paths in the circuit. So in this case, let's say I make a loop. And along this loop, I had an unknown supply voltage, but it gets used up. R1 uses 6 joules per coulomb, so 6 volts. It's proportional to energy. R2 uses up 12 joules per coulomb, that's proportional to energy. And R4 uses up 8. So that must mean that the battery put out 36 volts, 36 joules per coulomb of charge. And since energy is conserved, voltage is conserved here. That's loop law. Side note, since this is a bonus, this is the video, right? Charge is proportional to current. So the reason you have junction law, where like the current that goes in equals the current that goes out, is because this is saying the literal electrons that go in must be equal to the literal electrons that go out. Since current tells you how much charge per second, this 4 equals 3 plus 1 is actually a statement of conservation of charge, because charge goes with current. Yay! Okay, so that means we've gotten to a point where we can find box J. And since this is the video, I know you can get this by doing 3 equals 4 times 9, but since this is the video, I want to show you like a check that you can do. If I've done this problem correctly, then when I get the equivalent resistance, it should equal 9. So let's double check and see if we did this right. So I'm going to deal with R2 and R3 first because they are in parallel. That would be 1/4 plus 1/12, all inverse. In my calculator, when I do the inverse, that's 4 inverse plus 12 inverse. Get the parentheses out here. Inverse one more time. And that makes an equivalent resistance of 3 ohms for just this red and blue part of the circuit. Redrawing this in my head, this means that R1, R2, 3, that combo that was just the parallel that we simplified, and R4 are all in series with each other. And a 4, a 3, and a 2 in series with each other would be equal to 9, right? 4 plus 3 plus 2 equals 9 ohms. And since that's self-consistent, I can be pretty confident that I've done my work right. If I get to the end of the problem and solving for equivalent resistance gets me a totally different number, I know I haven't done something right and should review. Okay, so now we're to equivalent resistance. And you actually just saw me do one, so I'll show you one more. R1 and R2 are in parallel. So I'm going to deal with them first. R1 and R2, that's 1/2 plus 1/3, all inverse. In my calculator, that looks like 2 inverse plus 3 inverse. All inverse to be 1.2. R4 and R5 are also in parallel. So I'm going to do 1/4 plus 1/1 inverse. And I can do that in my head. So that's 1.25 inverse or 0.8. Now let's redraw. And when I do this redraw, I'm going to imagine keeping the battery exactly the same. I'm going to leave a little hole for where I'm going to put R12. R3 hasn't moved. R4 and R5 I'm going to replace. R6 hasn't moved. Now I'm going to replace R12 here. That was 1.2 ohms. I'm going to replace R45 here. That was 0.8 ohms. Together with R3 was 3 ohms. This means the equivalent resistance is now all in series. That's R1, 2, 3, 4, 5, 6. So maybe I write all those numbers, maybe I don't. This would be adding together because they're in series. That means 1.2 plus 3 plus 0.8 plus 0.8 equals 5.8 ohms total. The end. And when you get to the end, feel free to scroll back to the objectives, and check that you've reviewed everything. Some items that I know people are less likely to review would be the connection between conservation of energy and loop rule, conservation of charge and junction rule, as well as drift velocity, because they're not great like questions you're going to get tons of math problems on, but they are things that you should be able to answer multiple choice and short answer upon. All right, everyone, this answer key with additions made for, nicer, prettier, better handwriting will be posted on Drive. This video will be on YouTube. If you're watching it right now, you already know that. All right, thanks everyone. Bye.